what makes and what breaks a high performance home. I was hoping that this webinar will be a very practical thing with hopefully some take-home messages for everybody. I specialize in solar passive design, and typically I'll be using pretty conventional materials to achieve that. And so this really is, hopefully for most builders, there will be something in this talk that will, help you get a little bit more out of the materials that you're using. Okay, so it's about what are the big ticket items to pluck as you go through the construction process, and what are the pitfalls to avoid. I should just start by saying that when I'm talking about high performance home, I'm talking here simply about a house that is comfortable for clients, but very energy efficient, cheap to run, and potentially zero carbon or very low carbon. So that's what I mean when I'm talking about high performance. I do understand that sustainability is much broader than that, but that's what today's talk is going to be on. Would you like a carbon zero home? So this is really where we need to get to as an industry, that builders and designers for that matter are asking this question of their clients and are confident that they can deliver this for their clients. The world needs to move to a low carbon future, and the building industry is one of the higher contributors to the carbon loads at the moment. So the onus is on us to do something about it. The good news is that the technology and the price points are right. If you haven't already seen my first talk, the roadmap to carbon zero homes, that is up on the Builders Declare YouTube site, or you can find it on my website. And that really gives the argument, I guess, for zero carbon as something that is cost effective and in fact saves clients money now, and obviously saves the environment a lot. Building industry and legislation are heading this direction already, with changes potentially to NatHERS, whole of house, and the trajectory for low energy homes. There's a huge potential savings for the environment and the client for that matter. Just in Victoria, the average home produces 8 tonnes of carbon dioxide through emissions associated with the energy it uses, and a carbon zero home effectively saves almost 8 tonnes a year for the life of the house, not to mention the cost of buying that energy for the client. Warmer, more resilient, quieter homes. So these are all directions that things are heading, and what this leads to is a big opportunity for builders really to get in now, to learn the systems and the processes and to upskill their team so that they can provide to the market a very low carbon option, which has all these benefits. However, with big opportunity comes big responsibility. You don't want to be in this position as a builder. You've offered a whole lot. There you go, 9-star home, and they come to you and say it's not good to be in. Or it might be nice and comfortable inside, but look at the bills, right? So something has gone wrong in that situation. So again, that's what we're looking at today. So as we go through, you'll see on the slides a little apple that represents the low-hanging fruit to grab as we move through the build processes. And the other thing that you'll see is a little coyote. These are the pitfalls that you might want to avoid. Now, the place to start is the place I started the last talk as well, and that's really looking at where energy is used in the average home. So this is the average. If you had new homes, existing homes, you average them all out. This is the data that you get, and this comes from the Residential Baseline Study in 2015 for Victoria. If you're outside Victoria and watching this, if you go to this website, you can potentially download the data yourself and you can make your own nice little pie graph for your state. But it is good to know where your energy going in Victoria, and this will be the same, by the way, in Tasmania and the ACT. Most of your energy will be going to space conditioning, and most of that is into heating because we're in a climate where we need to heat most of the year. And these other ones, water, appliances and cooking, they're pretty static all through the states of Australia, a little bit of variation. This pie, like I said, well, for Victoria, we have the dubious honour of being the most carbon intensive housing in Australia, mainly because of the brown coal we burn in the grid. But the average house produces 8.8 tonnes of carbon dioxide a year, has a combined electricity and fuel bill in Melbourne of 2,686, might have changed a little bit. This is a little bit old, this data. And this represents the average house size of 200 square metres. All right. So the approach I'm going to take here is to work my way around this pie, a little bit like the last talk, but in this one, it's going to be a little bit more practical what to do and what to avoid. I should say at the outset, when I put together this talk, I actually found that there was a lot to say. And so this is actually going to be a two-parter. The first part that you're seeing today is really looking at construction and the shell and the fabric of the house, and really this space conditioning side, how to minimize that as a builder. And then the next talk is really looking at the technology that goes in the house, which really looks at the other side of the pie and how to minimize that. So if you do like this webinar, look out for another one down the track. All right, so to minimize space conditioning, what are the big rocks? What are the apples to grab here? So there's basically three main things. The first one is do a good design. And when I'm talking good design, this is the National House Energy Rating logo. So for most states in Australia, you have to achieve a 6-star minimum for your NatHERS rating report. New South Wales has basics, so they have a slightly different system. But all this is, the number that you get here is just a relation or it's just a score of how passive or solar passively designed the design is. That is how well it uses the climate that it's associated in to provide its own heating and cooling before you have to bring in mechanical plant to do it. So that's obviously one factor and makes a big difference. The other factor that goes along with that is construction that is of a quality and to meet the assumptions that the house energy rating software assumes. So we've all heard the story of a 9 or 10-star home that's built in a 2-star way and it'll end up being a 3-star house. So construction is vital, important. And the other component that goes into this space conditioning wedge is the mechanical heating and cooling system that you use and the efficiency of that. All right. So the first big apple is passive solar design. Now, this talk is not about passive solar design. That's a whole nother topic I'm happy to do at another time if anyone would like. Put your comments in the comment section if you'd like to hear that talk. But for most builders, we often won't get an option. We just build the jobs that come along. Most builders aren't also involved in design. But if you aren't involved in design, this is the only slide to passive solar design. It makes sense. I would aim for at least 7 stars. That's reasonably low bar to go for passive solar design, as long as you've got a bit of sunshine. And the other thing that I'd say that is vital to getting a high score is to go to one of these guys, a TPA, a thermal performance assessor. Go to them while the design is still fluid. Once you've maybe got your just the design concept that you and the client are happy with, before you've done town planning, before you've done engineering, before you've done working drawings, before that design is locked into concrete, and too much water has flown under the bridge for any real changes. And ask that thermal performance assessor, what can I do to improve what is already my best passive solar design that I think will work? What else can I do? And the thermal performance assessor will probably love you because 99% of the industry just use them for compliance purposes right at the end of the build. And all a TPA can do at that point is, if the house isn't already at 6 stars, they can maybe bump up wall insulation. And if that's still not at 6 stars, you start double glazing windows, and that's pretty much it. But the software can do so much more. So anyway, that's the first big apple for you designers out there. All right. Now, if you do the minimum of a 6-star design, compared to the average, which includes existing homes as well, if you can build it to that 6-star level with your building technique, you've already made a huge dent, basically a quarter of that 8.8 tons in Victoria, or approximately 2 tons of greenhouse gases you've just saved there, and some cost for the client. And that's just working to the minimum. Which is easy to design, harder to build. So we'll get into that. Now, if you go further and you've got a design, you're lucky enough to have a design at 7 stars and you build to that, that has a bigger effect on space conditioning. 8 stars and even bigger. You've got a very small amount of energy now needed for that house. And 9 stars, smaller again. And 10 stars is theoretically a house that needs no mechanical heating and cooling. Now, a lot of builders will be looking at this and thinking, that'd be great if only a 10-star design or a 9-star or an 8-star would come across my desk. I would love to do that. If you're that person, you should be linking up with some good sustainable architects and designers and letting them know that that's your passion. And however, if you're like most builders, you'll be building a 6-star or a 7-star house. But have no fear. Do not feel like, there's no way that you can make a significant difference. The technology is such these days that technology has a huge impact on the rest of this pie, which we will get into, perhaps more in part 2. All right, so for builders, once you get a design across your desk, and what you need to do is to fulfill the assumptions of the house energy rating. So at the very minimum, you need to meet the house energy rating assumptions. These are the house energy rating assumptions, which is good to go over because I bet no one's ever gone over them with you before. The first one is, well, make sure that the following is on the rated stamped plans. Now, by rated stamped plans, you should see in the plans that you're about to build with a stamp like this to show that those plans are the plans that went across the assessor's desk when he was looking at it. If you don't find a sticker like this or a stamp like this on your plans, stop what you're doing, go back to the designer, ask for the plans that have this stamp on it, and go and check that nothing has changed from the stamped plans to the ones that you're going to construct, because otherwise you are, building outside code really. And if there is changes, those plans will need to go back to the assessor for just a correction to the house energy rating. So the first step here is that house form and materials must be the same. So check your plans that the house form and the materials are as per the stamped plans. The next one is that the insulation is to the correct R. It's non-compressed throughout the build and it is complete. There are no gaps and cracks. So the house energy rating system assumes basically perfect install there. We all know that rarely happens on site. Once again, those correct R values, they should be on the stamped plans. If they're not on the stamped plans, you can scan this little QR code here and you'll bring up the actual report and you can see what the house energy rater put in for the different wall types in the house. All right, the NatHERS assessment also assumes that there's no thermal bridging, so there's no weak points in the house. It assumes that the building is reasonably tight. So that's reasonably tight by NatHERS is 10 air changes or less per hour at 50 pascals of pressure, which is approximately equivalent to about a 30 kilometre an hour wind blowing over your house. Now, I know those of you who are listening who are into passive house construction will look at 10 air changes and say that is a very easy bar to get under. And the answer is yes, that is a very easy bar to get under. Unfortunately, as an industry, we are not in general getting onto that, and I'll show you a graph a little bit later. You've got to check that the windows are as per the energy rating report, and that lights and extraction fans and the electrical plan is actually as per the stamped plan. That's this stamp on the plan. So once you've checked that and you start your construction, the first apple, right, the first low-hanging fruit is really to think about the thermal shell. So as well as thinking about structure, as well as thinking about detailing, as well as thinking about aesthetics and function, and schedules and costs and budgets, all those things that builders think about the thermal shell as well. So the thermal shell is simply the external skin of the house through which you get, energy transfer between the inside and the outside of the house. And you're trying to maintain a comprehensive thermal shell so there's no weak points. What does that actually mean? It means that either you're standing in your frame once you've framed up, and you're imagining heat flow and you're looking around, you're trying to work out where there's going to be weak points. Or even better, you're doing that in your headspace when you're looking at your plans and your engineering, and you're noticing, the energy rating is called up an R4 bat. Is there actually enough space to put that R4 bat in with the engineering that has been called up for this? It's a 90mm rafter. Can I get an R4 in that? No, is the answer. So thinking your thermal shell, trying to problem solve early on. So let's go through some elements of the house. Floors. So a lot of standard construction is using slabs, and we use slabs. We use it because slabs are a cost-effective way to spread thermal mass evenly throughout a house. And they also have, that's beneficial because if you've got a bit of thermal mass in your house, it takes a long time for that to heat up and cool down. And so the outdoor temperature can be going up and down. It can be a bit erratic, but you'll get a much more constant temperature inside because of that slower movement of the mass. The other thing, the other reason that putting a little bit of mass tends to give you a higher performing home, not always, but tends to, is especially now with very cheap solar panels, or relatively cheap solar panels, and very efficient heaters, so efficient reverse cycle air conditioners, is that you can treat that mass a little bit like a battery, and you can actually, it's not particularly related to the rating, but it's related to the performance. If you've got solar panels and you're producing that power, like on a day like that in winter, you can be heating your home, and the concrete will actually be absorbing that heat as well as the rest of the house. And when the sun goes down, you can turn off your heater and the house will retain that heat quite well. The contrary will happen in winter, and you will retain your coolness quite well if you've been air conditioning during the day when you're making heaps of power from the solar panels. Now, I write here insulate slab as a bit of an apple. Now, obviously, you've got to follow the plans that you've got if you're a builder, but it's worth asking the engineer, if there's no insulation, can we put some underneath? The reason being, it usually lifts the performance of the house by about half a star, simply because it delays the heat loss from the slab to the ground. It just delays that process and gives you even more of a lag, so that it holds those temperatures deep into the night rather than losing them quickly from the house once the sun goes down. So, but the other thing, the CSIRO recently came out with a little paper about groundwater and the effect of groundwater on the conduction beneath a slab and the performance of the house. So if you've got groundwater, say a water table within 5 meters of the home, it has significant 5 meters depth of the house. It has a significant effect on how quickly heat is sucked out of your home. So a bit of insulation underneath a slab does have a benefit. And that's even considering the discussion we had last time about my misgivings of end of life and polystyrene mixed up with concrete and recycling. Even with all that, I still think the performance benefit is worth it, and definitely the comfort benefit. All right. that was the good thing about slabs. The downside of slabs, here's a downside. If you have a slab like this where you've got a very high edge, you can see it's high edge, and often you'll have that because of, I think in this case, it was a flood prone area, or near a beach with sea level rise and that sort of thing. Anyway, either way, you can see it's got high side. Now, you can imagine a frame going on this and insulation going in that frame. The house can be designed and insulated really well. But at night time, you might get 5-degree temperatures outside. You might get 0-degree temperatures outside. And those slab edges will get very cold and they will just suck heat out through the side of the slab and out. And here, by the way, this no doubt will be a very aesthetically and beautiful house. However, I have some misgivings about whenever this sort of thing happens where you've got an outdoor paved area directly butted against a concrete slab. Usually it's not detailed, usually it's on ground. But I would always suggest you do it as a secondary pour if you can, and put a bit of Abelflex in between as a thermal break. Otherwise, what again will happen at nighttime in winter, this whole area will get very cold and it will just suck heat out underneath what I assume will be some doors, double glazed doors probably through there. Okay, so what's the solution to this to avoid avoid falling like Coyote there? Consider slab edge insulation if you've got high slabs and you're doing a slab. You can explain to the owner the problem of losing heat out the side of the slab, and that over the life of the house, this will definitely be a good beneficial thing to do. You can also feel it if you're on a concrete slab and you're walking around in bare feet, as I like to do on our polished slabs. You can feel it if you get to near the edge of the wall, that the temperature drops markedly if you don't have a bit of insulation in. Not so important if this is only a minimum freeboard of 200 mil, 150 mil, doesn't really matter. But once it's getting high, heat loss is related to area of that heat can get lost through. So that's when it becomes more important. What I've put on here is a bit of North insulation. I think it's North, maybe Knorf. It's a 50 mil climber foam, they call it. It's an R1.8 board. I've gone over the top here. It's in a termite zone. So this is just gone over with some termi mesh, and then we would render that later. If you're doing timber subfloors, this was a renovation, but if you're doing timber subfloors, if you've got some plans and it doesn't show insulation under there, if you possibly can get under there, it will always improve the rating substantially, at least a star usually, by getting under there and insulating. And if it's not on your plans, but you can do it, most owners will be up for a variation, because most people have lived on timber floors and know what cold timber floor is like. So what do I use? Typically I'll use green stuff insulation. It's got some recycled content, comes in a nice long roll, a bit easier. It's not a fiberglass, so it's not itchy. It's a bit easier for my guys to use underneath the house. R2.5 or 3. If you go much over that, the benefits start reducing or not paying themselves off in the house energy rating simulations. All right, let's look at external walls. So the first defense to unwanted air ingress into your home through your walls is the reflective foil, or the membrane that you use. And it's good to see more and more often you get the situation where you're starting to see foil being taped, foil being lapped properly. I still see it not always taped to the windows properly, not always taped to the doors, but you're trying to just create a monolithic facade so that there's less spots for the air to get in. Now, this is my first defense rather than my cladding, because claddings typically have a lot of gaps and cracks to them, and they're not made to be airtight in any way. And as a general rule, I like to batten off my cladding anyway so that it can breathe on the backside. Just helps prolong the life of the building. It also gives, if I've got a reflective foil like this, and the blue side is also reflective in reflective foil, not quite as much as the silver side, but it still has a reflective component. And whenever you got reflective foil onto an airspace, you get approximately another half an hour rating. So in your wall. So anyway, that's how I build. Now I've got down here just a note. So your vapor barrier is doing a couple of things. One, it's stopping direct air being blown in, but it's also typically you want to choose one that allows the wall to breathe. So anywhere below the tropics, so definitely in the southern half of Australia, what you want is you want your walls to be able to breathe. So if they do get wet inside, if you've got leaks that wet the inside, those leaks can dry off and it doesn't lead to rotting. More importantly, perhaps, is once you've actually finished this wall and finished this house and people are living in there, they're breathing, they're showering, they're cooking. And in our climate, the indoor air is typically more moist than the outdoor air. And so you get a movement of moisture through gaps and cracks into the wall cavity. And partway through that wall cavity, what happens is the temperature of that moisture-laden air on nighttime in winter, it'll get colder and colder and colder, and often can get to a point where it's condensed down and you get a dew point and the water condenses out and you get dripping inside your cavity. So you want a facility for those walls to breathe on and allow that humid air through. And if they do get wet, that they allow, once the sun comes up the next day and the wall heats up, that moisture can evaporate away. The other thing that some membranes are doing, they'll also have a water, they'll also act as a water barrier. And potentially, if you're a clever builder, you could be starting construction on the inside, maybe before you even finish your cladding, because you're working with a water barrier. Here's a nice little idea. If you just typically run your foil from bottom to top plate, you will get gaps at the top. Where air can come in over the top of the eaves and down the wall. So this is just a little idea of running a starter strip. Yeah, you can see a picture of it here. That can just be put on as you're doing the framing. Later on, once the framing's done, you can then, stick to that or use that as a start, and that sort of closes that gapping up the top. I do want to point out here, where I'm circling at the moment, this detail is wrong. You should always make sure your upper foil is lapped over the outside of your lower foil in case the tape breaks over time. I'm also a little bit dubious about this particular detail going in underneath the wall. Definitely don't do that if you have a slab. Yes, not good, but I wouldn't know. All right, next slide. So that's the first part of the barrier. The next part in your walls to get right, to build a high performance home, or at least a home that is performing to the star rating, is to put insulation in a non-compressed manner to the right R value. And if you look at this wall, this looks lovely, but the builders out there will be noticing that the studs are very uneven, obviously carrying different loads or picking up claddings or whatever on the outside. They're not running at easy 450 centers. Each one of these bats has been cut to fit, right? So they haven't just been jammed in and compressed in that process. And if you look down the middle here, someone's gone and actually put it nicely into that small gap. I might foam that with an expansion foam, but either way, this is what the software assumes, right? So it's worthwhile telling your installers to slow down and paying them, a few $100 extra to do that. Most installers these days get paid per square meter, and so they do as fast as they can, and that's just a recipe for a slapdash job. So explain to them there's a high performance house, and just get them to do the job, in a proper manner. If you don't, this is a very common scenario. Here you can see this is an image taken with a thermal imaging camera, which are excellent to get. And you can see the warm sections of the house, 19.8 degrees C in these orange sections. But you can see it gets very cold in the black and the purple. And what's happening here, maybe these bats haven't been quite pushed to the top plate there, and maybe these ceiling bats have not been overlapped over the top plate. Now, this is quite common, especially if you have a situation where you've got rafters that pitch onto the top plate there. If those are only 90mm rafters, say in a truss sort of situation, you might not have very much space actually directly above that plate, and the R rating might have been called up as, you know, might be an R4, might be an R6 for that matter. You know, you might technically need 300 millimeters of lofts of space up there to actually maintain the loft in the insulation. And you won't be able to do it. So these are the sort of thing that I was talking about. Think about the structure and how you're going to maintain. What you might need to do in that case is you might need to get some denser foam boards perhaps, and put them along the perimeter of the house to maintain whatever the R rating is that you had to maintain. The other thing that you might need to do is to bump up the R rating in the other bit to compensate for the less R rating around the edges. It's a bit tricky to do that, and you might need the house energy rater to help you make that assessment of what you need to do. The other thing to note here, you can see the dark, the blue coming down the walls. Now, I bet that there's bats in those walls, but you know, they might only be R1.5 bats, not filling up the whole cavity. And so you're up there just draining down the cavity and making that plaster cold. And it'll be a very cold corner to be in. So I always like to maximize my typically 90 millimeter cavity space with an R2.7 or an R2.5 bat that is 90 millimeters thick when it's fully lofted, so that it tries to stop those sorts of flows of unwanted air through the structure. This is another thing I do if I've got eaves sticking out to stop the cold breezes coming through the eaves. I just get half a bat and just squash into the space. Now, is this going to be as good as doing you know, passive house wraps inside? No, it's not going to be that tight, but it'll be a lot tighter than having nothing there and then your eave sheet on the outside and air just getting in between the gaps in the soffit there. The other thing to note here is I've got a can here of expanding foam. All of your penetration, so all of your door and wall openings, the frame, there always has to be a gap between the actual door or window and the house frame itself. Now, usually that is just left as a gap. And so that represents a weakness in your insulation. And a number of years ago, the CSIRO came out with a statement that if you have 5% of holes, your insulation value drops by 50%. I'm not sure that number's exactly right, but it does derate very quickly if you've got holes. And the gap, if you added up all these gaps around windows and doors throughout a house, you'll easily have a square meter of hole that's just uninsulated. So get some expanding foam, blow that into the gaps, make sure it's a low density so that it still allows the movement differential that is needed in there, and then, you know, trim that off. And that's a good job for an apprentice or a, you know, carpenter to get into. All right, here's another pitfall. So you get your insulation people to come install your insulation, R2.7 to the walls, you're doing really well. You know, you're maximizing your 90 millimeter space, and then they do the ground floor and they go upstairs and they do the upper floor and off they go. And then you take a photo like this. And this is extremely common where the joists, that rim of around the joist is just left uninsulated completely. So obviously this house will just be hemorrhaging heat during winter and probably gaining a whole lot of heat, unwanted heat. Not only that, if there's no insulation in there and there's gaps and cracks, you're going to get cold air potentially coming into that cavity space and sort of swishing throughout the house and cooling the plaster, and it's going to be a nightmare. So what I would always suggest, get some insulation, put it in between the joists up there. I tend to also like to fill up my joist cavity. I use an R4 bat typically, maybe an R5, depending on the depth that I've got to fill. And that's partly to stop sound, partly to stop stratification of heat rising quickly to the upper floors, but mostly actually to stop if there are gaps and cracks in my membranes, that it then becomes hard for breezes to blow through the house. They have to, you know, really try. All right, another potential pitfall where your house could be let down in its thermal performance is through the studs. This is a typical Australian stud corner. It's got that secondary stud there just to pick up your internal linings. But you'll notice that there's a stud hole missing just there. Now, typically you'll frame up and then you'll put your reflective foil on, you'll put your cladding on around the outside, you'll do your rough ends of your wires and your pipes, and then you'll put your bats in. But at that stage, it's just impossible to actually insulate into this gap. And actually in practice, often you will see a gap. It won't be quite as tight as that. You actually see a physical gap into there, and you wish you could insulate in, but you can't. And you'll just get potential breezes blowing in through there instead. Much better idea to use a 3-stud corner, a Canadian corner, some people call it, where you can tuck your insulation behind, or just fill up that space with an extra stud when you're doing your framing. Another typical weak point that I'm always having to induct my insulation installers about, because they always send somebody different to install, is power points. Electricians do not need holes cut out behind power points. I've checked this with a couple of electricians. It makes it a little bit easier for them to do their wiring, but there's no need to do that. And it's definitely a bad thing, especially on external walls. With a gap like this should probably be foam filled as well. So just make sure you induct your, your insulation installers that they don't need to do that practice. Having said that, if you're dealing with old wiring, the black stuff, that stuff can overheat. So if it's a really old house, check with an electrician before you go ahead with that. But as far as I'm aware, the white cable is fine to have in contact with insulation. All right, in a roof space, this is another spot of potential leakage. Here we have a skylight with plaster shaft, but we've insulated around it. But if we'd just left that as plaster, the roof space gets really cold, it gets really hot. It would warm or cool that plaster, and that would pass on and down into the house below. So make sure you insulate with the ceiling insulation your skylights. Likewise, if you have a roof, a little dummy wall or a dwarf wall into a roof space, you should run whatever you use for the roof insulation. That should go up that wall, up through the rafters. Don't just leave that as plaster, or else that room won't perform well. You've got a weak point in that thermal shell. This is a manhole. Make sure you insulate your manholes. Don't just leave it as a cut piece of plaster that can just slide around there. And also put a little bit of weather stripping around the gasket there, so it's a nice tight join. All these little things add up. This is a typical bugbear of mine, though things are starting to change. So this is a roof, and this is very typical, roof with downlights. You can just see the round circles. Those are downlights. Now, in the past, at least, to install downlights, electricians were required with halogen downlights to remove insulation from around those downlights by 50 mil. But of course, no one measures and cuts. What they do is they'll do their cutout, they'll reach their hand up into the cavity, they will grab, and then they'll pull. And as you can see, you can quite easily pull out almost half a bat doing that process. It means you won't have a fire, which is good, but it completely ruins your insulation to that roof space. Luckily, the fashion has changed, and I really recommend pendant lights that hang down. You need a lot less of them to light up the same space. You have a very small hole where the wire comes through, and you can run your insulation straight over. If you have a plan though, and it has downlights in it, and the owners don't want to change, talk to them about it. But if they don't want to change, then make sure you use a downlight with an LED downlight, first of all, with an IC or an ICF rated downlight, which says abutted and covered, or has a symbol like this to show that you can have insulation over the top of it. And then also induct your electrician that don't pull out, don't go and pull insulation. Of course, you might have to really help them, or make sure when you're doing the plastering that you pull the wires out on the right side of that insulation, and that it's easy for the electrician to get the wire if you want them not to muck around with your insulation. This is another common pitfall area. This is all standard construction, which I'm sure everyone's very familiar with who builds in standard ways. But if I've got, say, there's a flat frame ceiling, there's my 190 rafter, maybe it's 240. Typically, I'll probably put an R4 bat in there, and I've got an R1.8 building blanket on top of that. So what's that? 5.8 R of insulation. So pretty well insulated. But look, you come along here to where the box gutter is, and you don't have as much space. Now, either you compress the insulation down, in which case it's no longer achieving its R4 status, or once again, you're looking at a denser product. You might use a dense wall bat, or a couple of layers of R2.7 or something might fit in there into that space. But these are the things you should be thinking about when you're thinking about your structure. Here's another image from my thermal camera. This is before plaster's gone up, by the way, so you're not magically seeing through the plaster here and the insulation. But what you can see is really hot sections and cold sections. The cold section is the underside of the reflective foil, so that's doing its job well. But look at the roof battens. These roof battens here, there are metal top hat roof battens connected directly to the roof above through the roof blanket, and metal conducts really well. So effectively, my R1.8 blanket in that case is short-circuited. I mean, if this was my job, I would still have an R4 bat in there. So we've still got plenty of insulation. But once I saw a picture like this, I've just made sure that we always use timber roof battens just to get away from steel, because steel conducts 10,000 times better than timber. Just a little tip. Of course, if you've got a steel frame, you are potentially in trouble. Now, steel frames have a lot of benefits. They are recyclable. They are termite resistant. You know, they've got things going for them. But if I was building with this, I wouldn't want to be putting plaster on one side and then clad directly on the outside. All the heat flow will just bypass any insulation you manage to get in these strange little triangle-y bits. So in that case, you'd be wanting to put insulation on the outside and definitely have thermal, thermal break between this frame and whatever's going on the outside. Looks like it's a brick veneer, so there will be a bit of a thermal break, but still, I'd want a nice big cavity so that I could put some maybe some foil board or some Kingspan product on the outside. And this sort of thing I see a lot. Structural steel, even in timber frame jobs, you're always going to have structural steel. But what you want to try and stay away from, and what the software, the NATO software, does not take into account at all, is steel that passes from the inside of the building to the outside of the building. Here, definitely, this is going to be a feature steel, and that's connected straight to the steel there, which will go into the structure. Or they might be channels turned out like that as a design feature, but they're going to get very cold at night or very hot during the day, and that temperature is going to conduct its way through and into your house. So by all means do this, but say between this post and any internal framing, put a bit of timber if you can, or put some non-compressible rubber or something. Talk to your engineer about it anyway. How can you put some sort of thermal break between internal steel and external steel? I've got a camera exactly like this, and I swear by it. I think this is definitely, I consider it a low-hanging fruit for builders to buy one of these. It's just a little attachment that goes on the bottom of an iPhone. In this case, I think they've got them for Android as well. But taking photos of your structures really makes it real for your team. They can see why they're doing what they're doing. So, it's worth the $300 to $600 or so that you pay for this to get an infrared camera. And every time you do a different type of structure, take some photos, and you will improve as you go along, and your team will improve and upskill. And it really doesn't take long. I mean, it looks like it's really hard going over all those potential pitfalls, but once you know what you're doing, once your team knows what they're doing, it gets just second nature. All right, the last part of walls is, and standard construction, is the tightness membrane. Now, if I was doing a passive house, you'd be putting a wrap on the inside to stop air going through your wall. For standard construction that doesn't have that, you can treat plaster as a tightness membrane if you know what you're doing and you're trying to achieve that outcome. It's very hard for air to pass through plaster. It does diffuse through slowly, but once you paint that with 3 layers of acrylic, it's pretty much a really good air barrier. And of course, even if you have gaps in your cladding, even if you have gaps in your membrane, especially at the junctions between wall and ceiling, very hard to stop the gaps. If you have insulated your space as well and you have a very tight plaster, there's nowhere for air to come through. So if there's no path for air to come through or less path for air to come through, the air's not going to come through. Now, I'm not talking about trying to get standard construction down to 0.6 air changes per hour as per passive house. Not trying to do that. I'm trying to achieve, and this won't, I don't think you can do it. But you don't need to achieve the NatHERS rating and the benefits of the NatHERS rating. You simply need to get down below the 10 air changes per hour. And I do have a graph, like I said, that I'll discuss that in just a sec. So if you're treating your plaster as a tightness membrane, you obviously want to minimize the number of holes through the plaster, because this sort of thing isn't going to be a tightness membrane, especially if you have holes on the external wall. Now, if you're a builder building someone else's plans, probably you will have PowerPoints on the external wall. You could talk to clients, try and get them to move things onto internal walls so that the external walls can remain tight or reasonably tight. Or you can, next job, talk to the designer, if you're using the same designer, and say, can you talk to clients, try and get things, services off external walls. Also, if you've got pipes and a lot of wires in those external walls, it's going to be hard with standard insulation to actually put it in, maintain the loft and not have it compressed. So if you can, keep holes, especially off external surfaces. Instead of downlights, again, I would suggest pendant lighting there. This is just a picture of someone actually putting in some weather stripping on a manhole. Easy to do. Here's one people don't often think about. Steer away from cavity sliders. I've been into quite a few homes where when the wind's blowing, if I stand next to a cavity slider, I can feel air just gushing out that thing. Because effectively, it's just a hole through the plaster that leads up to the attic in this case. And attics usually aren't very tight, especially if they're tiled roofs. So either avoid these, though I understand sometimes you can't avoid them, and definitely if you're just following the plans, you're just following the plans. But what you can do is you can get some black builder's plastic, and you can wrap that sliding socket, tape it up before you put the plaster on, so effectively you don't have that hole, or it's much reduced. And probably the last bit of plaster advice I'd say is just get some foam, and once again, put some expansion foam along that little expansion gap that the plasterers leave at the bottom to allow for a bit of movement. And that just stops airflow coming down under the plaster and out underneath your skirting boards. And so you blow in some foam, trim it off. I take this a little bit further. I also look at pipes, especially ones that go vertically, and wires that go vertically between the levels, because I'm trying to stop air stratifying or the heat building up too quickly in the upper floor. It will build up anyway, but we're just trying to slow it down here. A little bit of spray foam. It doesn't take long for the team to do. Another place to foam is if you have wires on an external wall. So this was an external wall, and you've got an internal wall abutting it, you probably want to close those holes so you don't get airflow from the externals into the body of the house. It'd be good to just keep it in that wall if you can, or keep any air movement to that wall. And another thing to make sure that you've got in place is backflow dampers. A lot of fans, extraction fans these days will come with it. If they don't, make sure that you install these. I would always, by the way, be ducting to the outside. Do not duct straight to the roof space with the cheap fans. Effectively in your bathrooms, if you're just doing that, you're just putting moist air up onto your insulation, and it's just a bad recipe for failing insulation and potential rot and mildew and sick house syndromes, all sorts of things. So duct to the outside and make sure that you've got a backflow damper in there, so that you don't just get air swishing it and swashing its way through your duct work when you don't want it to. The old adage is, or the saying is, build tight, ventilate right. So this is just sort of following that idea. Now, I won't go into renovations, and that's probably a whole nother talk in itself, but only to say that renovations just up the onus on the builder to really think about air leakage and really think about weak points in your thermal envelope. And a great place to get acquainted with all this material is if you go to the Efficiency Matrix channel. I've stolen this screen grab from one of their YouTube clips, but it's a really useful resource for builders, and well done, Vincent and John, for that channel. We might leave that to one of our builders who do a lot of renovations to give a talk on that as well. Here's another low-hanging fruit. And like the thermal imaging camera, this is a great one for builders to do for themselves. Not necessarily for the client. This is really to give feedback. And you probably don't want the first time you're called on to do a blower door testing to be, when you're forced to, because that's in the contract. You want to know how tight you actually build, so you don't get big surprises. And so for those people who don't know what a blower door test is, basically they will seal up the house, and then they'll put basically this fan on the front door, and the fan just sucks out air, and then using a computer, they measure the resistance of that motor, and that tells them how much holes is in your house or how tight your house is. This is a super activity for a team to get involved in, because once they put this thing on, you can physically go around, you can put your hand up to the walls or to junctions, and you can feel where air is coming in. So it's just another one of those things that makes it real for builders where the holes are on site. So I would always suggest doing that. And if any of my team are listening, we need to do another one soon. It's good to do these things periodically to see how you're going. Question is, how tight should you go? A little bit of a controversial question. Well, in this talk, how tight you should go is definitely at least to this 10 air changes per hour, right? Because that's what the NatHERS software assumes. It assumes a certain amount of leakage, but it's around about 10 air changes an hour is what it assumes for leakage. Now, the CSIRO did some testing of this on new home construction in 2016, and they tested 20 homes in Melbourne, and I think the same number in other capital cities around Australia. They found some places like Tasmania did actually pretty well. Places like Melbourne did not do particularly well. And of the 20 homes they tested, I think one actually complied. So this is really showing a big underlying non-compliance issue in the industry. So there's a lot of tightening that we need to do with our standard construction. So this knowledge just needs to get out there. When I have done testing, I'm somewhere around this 5 air changes per hour, just using standard building materials. And I'm sort of seeing this 5 to 10 as some sort of sweet spot if you know what you're doing to aim for. Of course, I can see very much the attraction for Passive House with its air change down here of 0.6 air changes per hour, especially for designers and architects. They don't necessarily know who the builder is. The good thing about Passive House is that, part of the routine is to test at the end and to use these membranes. So you're very likely to get very tight structures. Maybe you won't get the 0.6, but you might be up at, 1, maybe 2 if you didn't do a great job. However, so that's very tight. You're going to be losing, less heat exchange. That's a good thing. However, if it goes too tight, you run into safety issues potentially. Passive House account for this, so don't throw up your arms yet. But you need you don't want to build up in your house with people breathing and living in the house. You don't want to build up of carbon dioxide. You don't want to build up of methane if you've got gas cooking and stuff going on. You don't want to build up of off gas materials, VOCs and things in your home. So you do want a certain amount of fresh air exchange with the outside. And typically 5 air changes is sort of a safe limit. Some people say below 3 air changes, you have to have heat recovery ventilation. That's what this line says, heat recovery ventilation, basically bringing fresh air in and transferring some of the heat from the incoming air to the incoming air as the outgoing air sort of goes out a baffle. I'm not sure you can see my hands doing a baffle, but if you don't know what I'm talking about, we Builders Declare did a one of these talks on passive house, so check out the YouTube channel on that. But if you are below this 5 air change limit, you definitely want to be safe and to have this heat recovery or energy recovery ventilation, sometimes it's called as well. So, but as a general rule, we need to tighten up our structures. If you build with standard materials, but you're thinking about it, you should very easily be able to get below this 10 air change hour and comply with your NatHERS rating. Oh, that's a heat recovery ventilation unit. That's what I was talking about. And yes, this was the talk that Hamish and Jesse did. So good job, Hamish and Jesse. And check that out if you haven't seen it. All right, so we've done all the structure now, the actual walls, the roof, the floor. Windows is probably is sort of the last thing that you've got to make sure complies with what the NatHERS assessor assumed. So how do you know? Well, it should be again.
Just a heads up, Jeremy. Sorry, we're just running a little over time, so just to let you know.
All right, thanks, mate. This is sort of the last last part of where I'm going today.
No worries.
Yeah, I see that 1 minute and 9. Sorry, 1 hour and 9. Sorry, everyone, if I've rambled. So with your windows, once you've insulated well, you're losing a lot of heat and a lot of energy coming into your house. It's coming through your window. So it's very important to get those right. And so look on your stamped plans, look at the window schedule, and it should say on the window schedule what sort of windows have been called up. In this case, it was the Koenig windows, and it should say a U value and a solar heat gain coefficient. Now, it won't look like this. This is actually the house energy rating certificate. So if it's not on your stamped plans, scan that little QR code or get your house energy rating certificate and see what the energy rater called up, because that is what you have to meet. There are 2 bits of information that you need to understand when ordering windows. One is this U value, and the other is a solar heat gain coefficient. There's actually other things, but these are important things I want to point out here. The U value is a measure of conduction, and typically you want a low conducting window because at night time for 12 hours a day, there is no sun shining, and you're just typically in the southern states, you're going to be losing heat out those windows. So you don't want them to conduct that heat away too easily. You actually want a good R value or a good resistance material. So you're looking for a low U value here, and solar heat gain coefficient, that's a measure of how much sunlight is coming through the windows. So typically, as long as you've shaded out for summer sun, you'll typically want a reasonably high solar heat gain coefficient. But when you look at your plans, what you have to order legally, you have to order a window that meets this U value or is lower, has to meet it or is lower, and it's within 10% of this solar heat gain coefficient score. So just make sure when you're doing your order for your windows that it complies with that. And that way you'll know that your windows comply with the house energy rating. One last thing that the NatHERS assumes is, unfortunately, they assume that there are typically no trees unless it has a preservation order on it or it's in a heritage zone. It won't have, it raters are required to assume no trees because they think trees die off and whatever over the life of the house, but they do have a big effect. So if you are surrounded by trees, I would definitely let your clients know that the rating doesn't assume trees. So it's actually going to perform different from the rating. And it's probably good in that instance to talk to the rater and ask them to actually model it up with shading from the trees just to see what the real performance is likely to be. Here we sort of got around it by just trimming the lower branches of these trees so that the winter sun can come under them, but it's designed so that the summer sun can give it full shade. So best of both worlds in that instance. And there you go, high performance construction with standard materials, or at least, if not high performance, at least high enough that it complies more or less with the NatHERS rating. And that way you can achieve this sort of performance with a 6-star or more with 7, 8 or 9. Now, next week, next time I do one of these, if you want to hear me again, and I'm sorry I've gone on everyone, we'll be looking at the technology. Do not despair if you only build a 6-star home, builders. With the right appliance and technology these days, there's been quantum shifts in the performance of things you can put in the house, and that can really make huge impacts into the rest of the pie there. And with that, I will say thank you everyone who has stayed on with me this long, and I'll hand over to Simon. Thanks, Simon.
Awesome, Jeremy. Thank you very much. We have a few questions, a couple of them private messaged, and I'll start off here with Ross. I'll only go through 2 or 3 just because we have ran over, but Ross has asked, how do you go about sealing the wrap to the slab? I'm sure that he's asked. And would it be bad practice to seal under your cladding against the slab, as it would stop the moisture escaping?
Yeah, so don't wrap it underneath the slab. I've made that mistake before, trying to do like a starter strip on both ends, and you just get water coming in underneath your base plate. Luckily, I worked that out quite early before the cladding went on, and we could just cut it and extend it. So your foil at the bottom definitely has to go past your base plate. Now, what do? I do nothing. I just run it past and that's it. And no doubt there will be airflow coming up from underneath my cladding into my wall cavity. However, my wall cavity is then possibly a bit tighter than normal because I've taken that time to try and get holes out of my plaster, and I've insulated it well. And so it's not that you have to be 100% to achieve good outcomes. I really want to get that across, but you need to understand where weak points are and how tight you need to go to achieve the NatHERS rating.
Perfect.
Does that sort of answer it? Yeah.
Yeah, I think so. I'll just go through one more here. So where was it? Do waffle pods act as insulation? Someone
Yes.
who's
Yeah, they do. So waffle pods, because I think he's asking because waffle pods have they're 110 millimeters wide, and then they have 110 millimeter bit of concrete, and it's sort of in this waffle shape. Do they actually act as insulation? So yes, there's conduction zones between the pods, and then you go a pod with very good insulation in a conduction zone. But what the software does, it works it out over the whole floor level of what the insulation value of those pods is. So the pod itself might have 300 mil of polystyrene and some air gaps. It might very easily be an R4 or something. But once you take into account there's bits without any pod in it that go down to soil level, over the whole floor, it goes down to an R.7, typically for a 300 mil pod.
Got you. One more has just popped up. What do you think about insulating internal walls?
I think it's really great for sound. I think it's also good for stopping any naughty, unwanted air leakage that somehow got into your framing system. And it's also good if you've got a cold room, say definitely a garage, you have to insulate off, or a bathroom or some area that you're maybe not always centrally heating. If there's a different heat profile in a different space, that should be insulated in between.
Beautiful. Well answered. Pleasure. Thank you, Jeremy. I think we'll get you back for part 2. See how that goes. There's plenty of wisdom there.
Thanks,
So thank you again, everyone that stuck around. Plenty of knowledge there. Hope it helps. We'll be back. Builders Declare will be back on April 14th with a presentation from Mark Thompson on sustainable timber, the Australian facts and solutions for the future. If you want to find out more about Builders Declare, you can email info@buildersdeclare.com. Check out our website, au.buildersdeclare.com. You can join us we've got a Facebook page, Facebook group, Instagram. We're everywhere where people are at the moment these days. So thanks again, everyone, and look forward to seeing you next time. Thanks, Jeremy.
Thanks, Simon. Thanks, everybody.